Hello everyone. In the last video, we already saw a few examples of similar figures. This paragraph is dedicated entirely to similar triangles. Now we've seen similar figures before. And when we had similar figures, we had to check two things. We had to check that all the angles matched, and we had to check that all the sides are multiplied by the same scale factor. And if we didn't check both of these, we could find examples that made them not similar. For instance, for some figure, it might have the same angles, but only be taller. Or it might have the same sides, but different angles. So we really had to check everything. Now with similar triangles, we get a very specific situation. Because once I have any line, and I know the two angles of the triangle, there's really only one triangle I can make. Because eventually they'll just meet in a point, and that is the last point. There's nothing else I can do. So where this was an and, we have to find both properties. Here it seems to be enough to check not even all the angles, but just two angles, because once two angles are the same, once I know these two angles, sure, my other triangle may be smaller or larger, but it will keep the same shape. So the two angles are enough. Now, what if instead of the angles, I don't know any angles, but I know the sides? In that case, well, I start with one of the sides. If I know the other length, it needs to be somewhere on the circle with that radius. Same with the other length. If I know the sides, then there's only one point that exactly matches those sides, and we can draw that with compasses. So again, if in this case I do need all three sides, but once I know all the three sides, once all the three sides are multiplied by the same scale factor, they immediately determine my angles as well. Even if I don't know those angles. So for the sides, we still need all three sides. If I change one side, it might be different. But I only need to check one of these two properties. The reason this works specifically with triangles has something to do with those special properties of the sine and the cosine and the tangents that we've seen before, and with Pythagoras. Even if these triangles are not right angled, some of those properties still hold. We can't calculate with them yet, but there are those special properties that only work in triangles. So triangles have this very specific property that we don't need to know everything to know that they're similar. And you will find in this paragraph, you're going to have to prove that triangles are similar without all the information. And then it's just enough to only check the angles or only check the sides. Lastly, as an intro to the next video already, that we only need to know so little information is very useful to work with those triangles, because I only need to know that two angles are the same, and I know they are similar. And for the record, there's a symbol for that as well. Almost forget. So just because those two angles match, I know that ABC is similar to PQR. So then if I know the sides of this, and only know one side of PQ, I can use the similarity to calculate the other sides. So that only works with triangles. There I can prove that they're similar and then use the similarity to show, to calculate new sides or to figure out more angles. But how to work with that further, we're going to see that in the next video where we really are going to apply this information. So I realized later on that I kind of skimmed over this symbol for similarity and that I should say a few more things about this. So first off, yeah, this tilde, this wavy symbol, tells you that, in this case, ABC is similar to PQR. And I've only done this with triangles here, but this symbol, first of all, also works with any other shape. So if I have some sort of quadrilateral that is similar to another quadrilateral, let's say DEFG, HIJK, then I can also say that DEFG is similar to HIJK. So it works for any figure, but there is one more thing to be careful about, which doesn't matter in these examples, but I'll show you another example where it does matter, which I'll do with triangles again. Because suppose I have some sort of triangle that is enlarged, but for instance, mirrored, like here. And I've gotten decay here, so let's just call this LMN, and let's use XYZ here. So here my angle L is the same as angle Y, my angle M is the same as angle X, and well, N and Z are the same. Then I have to list them in the proper order. So I can list LMN just like this, but I can't start with X because L is not corresponding to X. I need to list the corresponding angles. So L has to correspond to Y, M corresponds to X, and then we lastly have Z. So using this symbol gives us a bit more information. It tells us which angles correspond, but we do have to be careful to use that. With that information, you can get to work on this paragraph.